Okay guys, welcome. I hope you managed to print the chapter 4 notes. This is a new chapter called Linear Spaces, and I don't want to go into all the details of this section. You have shown me many times over the past 6 months that when you're absent you can catch up using the notes. I'm using Nick O's notes because they look nicer than my own, I have to say. But I want to talk in general terms of each of these parts in this section 4.1. It's a very long section, I think 6 pages, but actually it's not it's not as long as it seems. We're just repeating a lot of things that we've seen in the first 3 chapters because we adapt them now to different vector spaces. So the title of this chapter is Linear Spaces. In most textbooks it's going to be called vector spaces, but it's the same thing. What is a vector space or a linear space? It's basically things that behave like vectors. So things that you can multiply by a scalar and you get another element, like we get another vector when we multiply one by a scalar. Or you can add these elements together just like we add vectors to get a new vector. So this is why section 4.1 is going to be quite long in terms of pages, because we're kind of redefining everything that we've defined for vectors and say, hey, it works for other stuff as well. So firstly, the introduction goes over the fact that we've seen a lot of words that are specific to linear algebra or fundamental to linear algebra that we are going to redefine here for broader situations. So our kernel, image, span, basis, linear independence, etc., etc. There's more. These are the ones we wrote during that year when Nick O was in class. So here's a first example, and I think I hope you will appreciate what we're doing now, because this is really the transition from using vectors to the full power of linear algebra in a way. If you look at this differential equation here, you may, even without looking at what Nick O wrote, you may guess that sine x is a solution, because when I take the second derivative, so this reads f double prime of x plus f of x equals 0, and we're trying to find functions that fit here. You may have guessed that sine x works because the second derivative of sine x is negative sine x. So if you do negative sine x plus sine x, then it's equal to 0. So wonderful, we found that sine x works. You may then think that cosine x works as well. Well, yes, indeed, because the second derivative of cosine x is negative cosine x plus cosine x equals 0 again. And these are actually the only solutions, except you can multiply them and add them. If you look at y equals 5 sine x, well, the second derivative of 5 sine x is negative 5 sine x, so it works again. And if you tried with cosine x plus sine x, then it would work as well. So this is quite interesting. What happens is we can take sine x as kind of one vector and think of cosine x as another vector. And then with these two vectors, we can combine them in all the ways possible, and it'll give us all the solutions to this general differential equation. So we will use vocabulary for linear algebra to express these kind of things. So here we can say that f of x equals a times, this is a multiplication, a times sine x plus b times cosine x are solutions to the differential equations, and that all linear combinations of sine x and cosine x are solutions, which is really what we wrote just above. So closed under addition means that if you have a first solution and you have a second solution, you can add them together and it will still be a solution. Closed under multiplication, which is written below here, means that if you have a solution and you multiply it by a scalar, the result will also be a solution. Like I gave the example earlier of sine x, if you multiply it by 5 sine x is also a solution. So it's closed under multiplication. And you can say these two things in one to say that it's closed under linear combinations. So basically you can multiply any solution by a scalar, a or b, and you can add these together as well, and it will still yield a solution. So thinking about this as a vector space, we can determine that it has two dimensions. You can take any number of sine x, you can take any number of cosine x's, and combine them together. So sine x and cosine x are actually a basis of the space of all solutions. So if you look at an xy plane, you could think of the x-axis as the sine x-axis, and the y-axis as the cosine x-axis, and then you can choose any point or any vector in that space, and it would give you 4 sine x minus 3 cosine x, for example. Right here is something I'm not going to go into details at all, but it defines a vector space and a linear space, which are the same thing. Our textbook uses linear space. If you ever go to college and study linear algebra, chances are they will use the term vector space. There's a bunch of things that need to happen for a space to be declared a vector space, but all these things are natural for vectors. This is why we call it a vector space. It's because these things happen with vectors, and if it happens also with other types of elements, then we can also call that space a vector space. So what are these? If you add, I guess here there's a part missing. If f and g are both in the vector space, then f plus g is in the vector space. If f is in the vector space and k, then kf is in the vector space, etc. You can switch. So if you think of vectors, if you have vector v and w, you can also do w plus v, and it's going to yield the same. It's commutativity. There's a zero element, like there's a zero vector, etc. You can multiply a vector by 1 and it still gives you 1, etc. So if you think of complex numbers, you can see that it's a vector space because you could check all of those above, 1, 2, 3, 4, 5. Here it's bullet points. Nick had a better idea by numbering them, and check that yes, all of the ones above actually happen. We're not really proving it, it's just common sense. There's a neutral element because 0 plus 0i, if we look up here, if you add a complex number with 0 plus 0i, you will still get the same complex number. So this is an interesting example because it shows some kind of diversity. We already talked about the solution of differential equations that can be vector spaces. Here's another example that's entirely different again. If you have infinite sequences of numbers. So here's an example. 2, 4, 6, 8, 10, 12, 14, 16, 18. It's all the even numbers, and so on and so on. Here's another one that's completely random. -3, 7, 2, 8, 0, 0, 0, 1, -5, and so on. You can determine that if you have two elements in the vector space of infinite sequences, yes, you can add them, and you will still get an element from the same vector space. If you add them, which is what we do in B, you also get an infinite sequence, so it's closed under addition. There's no way you can add two infinite sequences and get something, and get a function. So you can also multiply an infinite sequence by a scalar. Let's take the first one we had here and multiply it by 3. Now 2, 4, 6, 8 becomes 6, 12, 18, 24. This is also an infinite sequence, so we didn't fall off the cliff. We still remain in the world of infinite sequences. Is there a neutral element? Yes, there is. If you choose the infinite sequence 0, 0, 0, 0, then you can add it to another sequence, and the other sequence will remain what it is. So questions that may arise with this, thinking of vectors, when we had two vectors in 3D, for example, we may have wondered, what is the span of these two vectors? Where can I travel in space with just these two vectors that are pointing in weird directions? And where I can go is a plane that kind of goes maybe in an oblique way through the 3D space. You can ask the same questions here. What are all the sequences I can make with these two? If I pick these two sequences here as a basis, then I can multiply all of them and I can add them together. What are all the possible sequences that I will get? Here's a kind of a diagram that is, it looks impressive, but really I've never found any kind of use to it. But it's kind of the way I interpret it is it's kind of a sequence of, if you have linear combination, then you are able to define what linear independence is. If you have linear independence, then you are able to define what a basis is. Well, you need these three things to define that. If you have a basis, then you're able to define what dimensions are, and so on. But don't worry too much about that. Now, subspace. If you know that V is a vector space, then you can try to find subspaces, so spaces that are smaller than the original space V. Just like when we were thinking of 3D space, we talked about the fact that if you take a plane through the origin, it's a subspace of R3. When you want to check that a subspace really is a subspace, then you don't have to check everything that we saw above, the long list of bullet points. You only have to check two of them. The reason is all of the others, you know they're going to be true because you are already working in a linear space. So if you're looking for a smaller one, many of them will be automatic. The only two that are not automatic are that the subspace contains the neutral element. You need to check that you picked a smaller set that still has the neutral element, and you need to check that it's closed under addition and closed under multiplication. So let's have a look. If we think of all the functions, all the polynomials of degree less than or equal to 2. So f of x equals ax squared plus bx plus c. Can we show that it's a subspace of all the functions? So here it is given to you that all functions form a vector space. So all you need to check is that 0 is part of this subspace, and that if you take two elements in the subspace, you will get something that's again in the subspace by adding them or multiplying them. Firstly, if you think of parabolas, y equals f of x equals ax squared plus bx plus c, if you just choose a, b, and c equal to 0, you will have f of x equals 0. So yes, the neutral element is in the subspace. And secondly, if I take two quadratic functions and I add them together, I'll still get a quadratic function. If I multiply a quadratic function by a scalar, I will still get a quadratic function. So I can see that polynomials of degree less than or equal to 2 form a subspace of all functions from R to R. These polynomials of degrees less than or equal to 2 are denoted P2, and if you should think about that. How many dimensions does it have? I'll give you 4 seconds. Well, it's tricky because it's not 2. If you think of f of x as ax squared plus bx plus c, you actually have 3 things you can choose. You can choose how many x squares, you can choose how many x's, and you can choose how many 1's. So there's 3 dimensions in the subspace of quadratic functions. Show that the subset of differentiable functions form a subspace of all functions. So if we look at functions that are differentiable, does it contain the neutral element? Yes, because f of x equals 0 is differentiable. And then if I take two differentiable functions, can I add them together? Can I multiply them by scalars? Yeah, sure, you can. If f and g are differentiable, then af plus bg is also differentiable, no problem. So now, again, something different, but we're using objects that we've seen before, matrices. We want to look at this a space of matrices. So normally the objects we worked with until now were vectors. The matrices were like machines. This is special in this example here. The objects we are working with are matrices themselves. And we wonder what are all the matrices that commute with 0, 2, 1, 3. Commute means that you can flip them and you would get the same answer. So, two things to check is the neutral element. Does the neutral element of 2 by 2 matrices commute with A? Yes, it does. 0, 0, 0, 0 times this is equal to this times 0, 0, 0, 0. And secondly, if you have two matrices that commute with A, then is it true that adding them will still commute with A? Is it true that multiplying one of them with a scalar will still commute with A? And the answer is yes. So here are the steps that you can study on your own when you copy the notes. By the way, this is true of any matrix. This is not a special matrix 0, 2, 1, 3. Any matrix A, matrices that commute with it form a subspace. All right, how much more? Well, all right, do non-invertible matrices form a subspace of R 2 by 2? It looks like it could be, because 0, 0, 0, which is the neutral element, is in there. It's non-invertible, so we are happy. However, you could find two matrices that are non-invertible, but once you add them, it becomes invertible. So how did we find these two examples? These are not the most obvious examples you can make up. A student came up with these. If you want a matrix to be non-invertible, you want AD minus BC to be 0. So this is non-invertible, this is non-invertible. However, when you add them, you get the matrix 2, 3, 3, 5, and that's invertible. So here's an example of something that is not a subspace of all 2 by 2 matrices. All right, so here are all the words that we know already. Believe it or not, a couple of years, or my first year when I was talking about that, I literally copy-pasted everything from previous chapters, and every time there was the word a vector v is called, or the span of vectors v1, v2 is the set of all, etc. I just removed vector and put element instead. Instead of vectors v and w, I called the elements g and f. But the concepts are exactly the same. Linear combination, span, redundant, linearly independent, basis, and so on. Here's an exercise with three different problems. We have to find a basis of certain spaces. So the first two, A and B, are pretty easy, and the third one is a little bit more technical. Question 1, find the basis of the space of 2 by 2 matrices and state its dimension. So the question is, if I want to make all 2 by 2 matrices, what are the foundational matrices I can pick? And the easiest choice is to choose 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, and 0, 0, 0, 1. I'm reading these vertically, but it doesn't matter. You can read them horizontally. It depends on the context. With these, I can make any 2 by 2 matrix. For example, I can take, it's like almost like a recipe. I take 2 doses of that, 3 doses of that, 4 doses of this, and -5 doses of that, and I add them together and I get the matrix 2, 3, 4, -5. So the dimension of the 2 by 2 matrices is 4. What about a basis of all quadratic functions? We talked about that earlier. Well, if I want to make all quadratic functions, the best basis I can pick, not the only one, but the easiest one, the most obvious one, is to choose f of x equals 1, f of x equals x, and f of x equals x squared. If I have these three, I can make all the others. If I wanted to make the quadratic function 7x squared plus 2x minus 8, I would just take minus 8 of those, 2 of these, and 7 of that. So how many dimensions does it have? 3. Lastly, we also saw the example with matrices B that commute with A. If we want to find all of them, we are interested in finding a basis, because if we have a basis, then we know that the span of that basis covers all the solutions. So to do that, we are looking for matrices A, B, C, D that have the behavior we expect, which is that they commute. So this is a bit of algebraic work. We distribute, we identify the entries, so 2b equals c, at the bottom here 2d equals 3 plus 3c, and so on. This gives a system of equations which you can solve using matrices. It suddenly becomes a bloated 4 by 5 matrix, but when you do that, just be patient and you'll understand what's going on. And in the end, we find that all the matrices that will commute with the 0, 2, 1, 3 matrix have this form here, which we can write like that. This is a very clever step because it allows us to see that, in fact, I can take 1, 0, 0, 1 and 0, 2, 1, 3 as the matrices in my basis. And then any linear combination of these two is going to give me a new matrix which also commutes. So, in conclusion, the dimension of that vector space is 2, and here is a basis of that vector space. Okay, yes, that is it. So lots of stuff. In summary, what we are doing now is expanding the concept from vectors to other vector spaces, but we are looking at vector spaces, which means things that behave like vectors. You can, and we will, for example, think of polynomials, quadratic functions. You can think of that as a vector. If I have the vector 2, 3, 4, I can identify it with the quadratic function f of x equals 2 plus 3x plus 4x squared. So the function f of x equals 2 plus 3x plus 4x squared can be seen as the vector 2, 3, 4. And if I multiply quadratic equations by a scalar, or if I add two quadratic equations, it will behave just like when I multiply or add vectors. All right. Well, I hope going over these notes and copying them also helps making sense of the things I went over quickly. And yeah, that's it for the notes. Thank you.